All right, guys. So I'm gonna be. Go ask mommy. Go ask mommy. I'm working. Okay, my daughter's right here. I'm going to be going through this and hopefully showing you guys kind of step by step how to do some of these math problems. I'm only going to do a couple of them because I think just a couple examples, I think you should be able to get it no problem. But the first one, of course, I'm going to rotate this. Actually, I'm going to do, well, I'll rotate it and then I'm going to do a screen capture. I don't know how well that'll work, but we're going to try it because I want to be able to write on the screen. So here we have what you're trying to do is you're calculating overall energy efficiency. And in order to do that, you have to know the components of the system. So in this instance, we're saying that coal, we're moving from coal to electricity to an LED bulb, which is a fairly common occurrence. I have LED bulbs in my house, so, and I am, hey, baby, I'm doing something. Go talk to mommy. Go talk to mommy. I'll talk to you in a second. All right, sorry guys. So obviously we get a lot of coal power in this area, so it's fairly common for our electricity to come from coal. You burn that thermally, it generates heat, it causes steam to generate from introducing water to the system. That steam spins a turbine and electricity is produced. That electricity then has to go from the coal, which is only 36% efficient, to the power line, so it has to move down the power lines to get to my house. The power lines are luckily 90% efficient, and then it gets to my LED bulb at the end at 25% efficient. So in order to find the overall efficiency of these values right here, all I have to do is change these percentages to decimals. So I'm going to say 0.36 times 0.9, okay, times 0.25, okay. So I'm going to hopefully move out of that into calculator. So again, I'm going to take 0.36 times 0.9 times 0.25, and I'm going to get a total value of 0.081. Multiply that by 100 to change it back into percent. It's 8.1% efficient. All right. So if I go back to this, assuming that I did my math correctly, that's right here in the middle. Sorry. It's going to be. I lost my screen right, sorry. It's going to be 8.1% efficiency. So just 8.1%, you're fine. Kind of moving down, thinking about the natural gas here, it says that natural gas, which is more efficient than electricity, to an incandescent bulb. Okay, so again, we're going to do natural gas at 60%. So that's our value here. So we're going to take, here, let's just save that. Okay, we're going to take this apparently not. We're going to take this 0.6%, or 0.6. We're going to multiply that by, sorry, I don't know why it's doing that, but we're going to take that, we're going to multiply it by, again, 0.9%. And we're going to multiply that finally by 0.5% or 0.05% because it's 5%, not 50%. So if we get that, again, 0.6 times 0.9 times 0.05, go back to our calculator, clear this one out, and we do 0.6 times 0.9 times 0.05. Really, the issue here is not the power generation. 60% is fairly good, much better than coal. 90% again is super efficient. It's the 5% that's really hurting us here. So we equal that out. We get 0.027. Multiply that by 100. And it's going to give us a total value of only 2.7% efficiency. Okay, so your total here would be, again, if I actually screenshot it so I can write on it, would only be 2.7%. So it's pretty bad compared to the other one. Again, I don't remember what the other one was. You'd have to multiply these again, but I think it was actually better, and it was mainly because this LED bulb at 25% efficient as opposed to the incandescent bulb at 5% efficient made it much better. All right, so if I go back to the original document so I can actually scroll down, sorry, it's kind of annoying. Let's go to the conversion practice a little bit, okay? This is fairly easy. For example, this first one, okay, we got to kind of remember these values here, but if I go to screen write on this, okay, this is going to give you a lot of information. Please use that. These are your conversion factors. So if we start with what is given, which is 6.85 kilometers, okay, we're going to do 6.85 km. We want to get to meters. So if I look at this, is there any of these that say kilometers to meters? Well, obviously there's the top one. So I know that there are, for every 1 kilometer, there's 1,000 meters. Okay, I'm trying to get to meters from kilometers. It's just a one-step conversion problem. It's fairly easy. So I'm going to multiply this by 1 kilometer per 1,000 meters. Now, I don't want to put kilometers at the top. I always, when we do conversions, we always want them to be diagonal so that the values, the units that you don't want, cancel out. So I want the kilometers, the 1 kilometer, to be down here at the bottom, which means that there are 1,000 meters up here at the top. So now I take 6.85, I multiply it by 1,000. I could just move the decimal place over 3 times, 1, 2, 3. So I'm going to get a 0 there. I'm going to end up with 6,850 meters. You can divide it then by the 1, but it's not going to change anything. So sorry, that's a 6. 6,850 meters is your answer. All right, so going back to this guy. Hopefully that's still going. It is. Okay, so let's do one more of these. We're going to go from centigrams to grams. So now I totally understand that going from centigrams to grams probably sounds odd. But it's going to be the same conversion. So even though it doesn't say how many centigrams are in a gram, you should be able. Yeah, I mean, I just want to make sure because it doesn't say it here. Okay, yeah. So you should be able to realize that we're using the same sort of values here. So if we say that there's, for every 1 meter there's 100 centimeters, then we can assume that for every 1 centigram there are 100 grams. So again, we start with 7. We start with what they give us. I'm going to go back to screen right. Okay. We start with 76.81 centigrams. Okay, and we're trying to get to grams. Well, again, centi always means 100. So I know then that there are 100 I see I want to put 100 centigrams here, but then they wouldn't be diagonal. So I want to change that to 1 gram per 100 centigrams. Okay, this isn't a value I normally work with. But now the centigrams are across from each other, so they cancel. I'm going to take 76.81, divide it by 100, and I should get my value. So I could just move the decimal place over 1, 2 times, or you can do it in a calculator. It's whatever you want to do. So I'm going to end up with 0.7681 grams. Now, if you wanted to change that to if you wanted to round it just to the nearest hundredth, you can change that to 7 or 0.77, so that would give you the same thing, 0.77 grams. This is a fairly large number. You can put a 0 out in front, whatever you need to do. All right, so I think these simple conversion problems are fairly straightforward, but I keep doing that. But let's go to one of the more challenging ones. Okay, and more difficult. This one's milliliters to liters. That one's fairly simple. Honestly, the one that was the oddest was the one we just did, the 76.81 centigrams to grams. But let's look at this thermal problem. It's all it is a conversion problem, and I'm going to try to do one of these for you. Okay, and you had to have a little bit of information. I told you that 1 metric ton of coal is 29,300 megajoules, which equals 29,300,000 kilojoules. So I kind of gave you some information there. If you read it, it says a British thermal unit, BTU, is the amount of energy needed to raise the temperature of 1 pound of water 1 degree Fahrenheit. This is the imperial unit. We still use it today. If you go and buy an AC, it'll tell you how much BTUs it offsets. It's kind of a silly thing. A calorie is a better use of energy, and we use that as well. We use it for food. It's because it's a national standard. It's the SI unit. So a calorie is the energy needed to raise the temperature of 1 kilogram of water 1 degree Celsius. 1 calorie equals 4.184 kilojoules. How many BTUs and calories are in 1 metric ton of coal and 1 liter of diesel fuel? All right, so we're gonna do the coal one. Why not? Okay, so what we need to convert it to is what the question actually asks, and this is really important that you identify what the question is asking. Okay, it says, like, highlight the important things. It says how many BTUs. So we're looking for BTUs and calories are in 1 metric ton of coal. Okay, and again, I'm going to ignore this one. You guys can do that one on your own. So I'm looking to change 1 metric ton of coal to BTUs and calories. In order to do that, I need to know this conversion. 1 BTU equals 1,000 or 1.055 kilojoules, and I need to know this conversion right here. These are your conversion factors. Okay, that 1 calorie equals 4.184 kilojoules. All right, so these are going to be really large numbers, just so you're aware. So you always start with what we're given, which is 29,300 megajoules. Everything is in kilojoules here, so I'm just going to keep it at that. So this should be fairly easy, honestly. But I'm going to, let's see here. I need to scroll down. So let's go back. I hate to keep going back and forth. I apologize. Let's go back to this so that I can actually kind of position it so I can write on it. Okay, so I'm going to try to put it there so we have a little bit of room to work. Then we'll do screenshot. Okay, so again, starting with what they give you, I need to know this, and I need to know this, and again, they're both in kilojoules, so we're going to start here with the amount that we have. 1 metric ton of coal is 29,000, or 29 million, excuse me, 300,000 kilojoules. Okay. Now that's a big number again, but we're going to change that first to BTUs. I'm going to say that for every 1 BTU, notice that I put BTU at the top, okay, because I want BTUs to be our end result. I want to find, remember it says how many BTUs and calories. That's what we're looking for. So for every 1 BTU, we get 1.055 kilojoules. Okay, now I'm going to see if I have a calculator so I don't have to go back and forth here. Of course I do not. So I don't have a calculator. I really don't want to go back for it because I think I'm going to forget like that number. But all I would have to do is take this 29,300,000. It's a big number, but I divide it by 1.055 kilojoules, and I would get that value. These would cancel, and I would be left in BTUs, which is exactly what I'm looking for. Okay. I don't want to. I'm looking to see if I have a calculator anywhere. I don't, and I don't want to leave you guys hanging. But let's set up the next one real quick. So same value. We're going to start with 29 million. I keep saying 300,000, and again we're going to have kilojoules, and we're going to multiply that this time by 1 calorie equals 4.184 kilojoules. So I'm going to say 1 calorie. Okay, I'm just going to shorten it to cal there. Divided by 4.184 kilojoules. So 4.184 kilojoules. Okay. Now again, the kJs are going to cancel out, and I'm going to be left in calories, which is exactly what I want. If you multiply that across, or excuse me, you multiply, or you take 29 million, can't do it, 29,300,000, and you divide it by 4.184, you will get the correct value there for calories. Now, once you, that solves this first one here, but you guys, I'm going to save this second one for you. It's the same sort of thing. You're trying to figure out basically how many BTUs and calories can be found in diesel fuel. Okay, and it gives you the same value. It gives it to you in kilojoules. And all you have to do is use these values here to answer it. So again, these are the conversion factors. All right. Hopefully that has been helpful. It was kind of thrown together, and I've never used this software before. I kind of like it, but I'm doing it on my cell phone, which is kind of unfortunate. Hopefully, though, that works, and you guys, this helps a little bit. If it doesn't, let me know. If you're still confused, let me know. If I made a mistake, because I'm not really checking myself here and I didn't have anything to go off of, let me know that too. Okay? Do what you need to do to make sure that you understand this. I don't foresee this being on the test, at least not. I might throw in a bonus, though.